While 62.5 micron fiber has historically been the major player in LAN deployments, 50 micron has become a major contender because of increasing bandwidth demands. It's not uncommon to find single-mode fiber in the LAN today. Selecting the appropriate type of multi-mode fiber for your application can be reduced to the following points and considerations, with a focus on, number one, reach and bandwidth. So you need to know which applications and protocols your network will be supporting today. Then examine which potential applications and protocols you'll use in the future. Then find out which wavelengths of operation are specified for your end equipment. Also obtain relative operating budget parameters, most notably the maximum power loss allowed in the channel and distant reach specified for a given data rate. Then match the system and electronics requirements with the appropriate fiber type based on specified attenuation and bandwidth parameters. Now, Table 1 puts different standards into the overall context of multimode fiber classification and lists how each corresponds with the other. OM1, that is legacy FDDI grade fiber, originally was designed for use with LEDs that operate at speeds below 622 million bits per second. FDDI, which is Fiber Distributed Data Interface, was a prevailing data transmission protocol when 62.5 micron fiber was introduced. It has since been displaced primarily by Ethernet. Corning Cable Systems still offers OM1 fiber as part of its landscape solutions set. However, for new installations, 50 micron fiber is the way to go. OM2 fiber enables maintenance and extension of 50 micron cabling. OM3 laser optimized fiber can support 10 gigabits over 300 meters and is recommended for all network builds with link distances up to 300 meters. And now for OM4, which is also a laser optimized fiber that further extends the capabilities of OM3, OM4 is not a new fiber type from the standpoint of design and manufacture. All major fiber manufacturers have been selling a fiber with an effective modal bandwidth, that is EMB value, equivalent to that specified by OM4 since 2005. You may have bought it, but you didn't know you had it. TIA-492AAAD now specifically addresses OM4 specifications. Prior to the standardization of OM4, this higher performance fibers were sold as part of OM3. That's why I said you may have purchased it before, but you just did not know it. IEC standardization of OM4 has yet to be approved, but we expect that most, if not all, of the specifications will be harmonized with TIA 492AAAD. Although addressing current application requirements should be the imperative with initial selection criteria, future network growth and unanticipated upgrades, whether brought on by advancements in technology or user population, should be considered. The small premium paid for higher performance fiber is worth the avoidance of having to recable later to support higher data rates. In addition, the incremental cost of spare fibers is also a wise safeguard against unpredictable network demand. Prevailing wisdom still dictates minimum percentage allocation of about 25% for most networks. The decision to plan for potential single-mode fiber may also be weighed because the current trend in laser transmitters is a declining cost curve. Standard single-mode fibers, that is non-dispersion shifted with a zero dispersion wavelength of 1310 nanometers, is still the workhorse for most enterprise requirements today that are not met by multimode fiber. The proper choice of multimode fiber is essentially reduced to a question of what distance can be reached at a particular transmission speed. The predominant data networking protocol in today's LAN, and now encroaching on WANs, wide area networks, is Ethernet. Table 2 lists both prevailing and legacy network protocols and applications that specify multimode fiber, with their corresponding wavelength of operation and distance capabilities. Highlighted rows are the most popular implementations in today's LANs and SANs, that is, storage area networks. It is worth noting that 850 nanometers is the primary wavelength of operation. That is because of the availability of low-cost 850 nanometer VCSELs. When referencing Table 2, it is important to understand that network communication channels can both be dispersion limited as well as attenuation limited. Both dispersion, that is optical pulse broadening, and optical loss, whether it be fiber attenuation or passive component insertion loss, they both affect overall system bandwidth. Now, bandwidth is essentially the information carrying capacity of the fiber and defines the maximum data rate over a given operating distance. Table 3 provides the bandwidth and attenuation parameters for OM-compliant fiber types that are specified in Table 2. For full explanation of bandwidth characterization in multimode fiber, please search our website for AEN 81. This is an application engineering note on multimode optical fiber bandwidth characterization. We also have a video on the subject. It is assumed that the overall power budget requirements are met in reaching the distance capabilities specified in Table 2 for the particular network protocol under consideration. These requirements may either be specified by the general specification for that network protocol or by the electronics vendor or manufacturer. Tight bends, sharp edges, over-tight tie wraps, staples, etc. are commonplace in most cable routes, ladder racks, and equipment frames. Strong consideration should be given to selecting a fiber that offers bend radius protection down to 10 millimeters and below. Those type of fibers are deemed ultra bendable and should be compatible with current optical fibers, equipment, practices, and procedures. Another consideration in choosing the correct fiber for a network is compatibility with any incumbent fiber, that is legacy fiber, that's already installed. Although Corning Cable Systems does not recommend mixing 62.5 and 50 micron fiber in the same channel, it is technically feasible. In theory, for an overfill launch condition, loss should be minimal when going from a smaller core to a larger core, the larger core being 62.5, but considerably higher in the reverse direction. Multimode fiber compatibility between fibers with the same core size but different bandwidth is another potential challenge when integrating new multimode fiber with legacy or existing multimode fiber installation. Per industry standards, multimode fiber cable plans should once again maintain uniform fiber types throughout the entire operating channel, including fiber link and any connecting jumpers or patch cords. Corning Cable Systems also stands by this recommendation. In situations where mixing fiber bandwidth types is required, it is possible to predict the expected performance deviation from uniform link specifications. Multimode fiber compatibility between different fiber types with the same core size but different bandwidth is another potential challenge when integrating new multimode fiber with existing plant. Per industry standards, multimode fiber cable plants should once again maintain uniform fiber types throughout the entire channel. That includes the fiber link and any connecting jumpers or patch cords. Corning Cable Systems also stands by this recommendation, but in situations where mixing fiber bandwidth types is required, it is possible to predict the expected performance deviation from uniform link specifications. Corning Cable Systems can provide general guidelines for such scenarios on a case-by-case basis. And that's it. If you have any questions, please give us a call or send us an email at cablesystems@corning.com. And remember, Corning Cable Systems recommends getting trained in fiber optic installation. We offer a series of classes, of course, and we thank you.